Hello guys, my name is Pablo, and we're going to talk about prime numbers and its relation to cybersecurity. Miguel and Melissa will follow on with me later. So prime numbers are pretty much everywhere around the world. I mean, they can be on your watches or scores boards in any sports. But it's not, at the same time also mysterious because there's still a lot more prime numbers to be found, which we'll later on prove. Even in recently, 4 years ago, there was the most recent number here. But prime numbers are also used in the encryption industry, and mathematicians along with computer scientists work together to make sure everything that we do in the internet is secure. So what are prime numbers exactly? Well, as far as an elementary goes here, prime numbers are natural numbers greater than 1 that can only be divided by themselves or by 1. Even numbers and certain numbers are known as composite numbers, which can be divided into prime components. There is also a college level explanation of this as well, which can extend a lot further. Now, when it comes to its history, it was believed that in the 6th century BC, Pythagoras and his students were talking about the relation to prime numbers. But it was not until 300 BC when there was a published evidence from Euclid in his book Elements, where he stated that there are infinitely many prime numbers. And there was a proof on that, and Euclid used his own fundamental theorem of arithmetic to prove his theorem, which states that every natural number can be written as a product of prime numbers. And he later went ahead and proved that with the theorem that he used, that there exists several prime numbers, or not several, infinite prime numbers. He also explained in his book on the process on how to create a perfect number using Mersenne primes, which means that there exists a positive prime p, for which there exists a prime q, such that p equals 2 to the power of q minus 1. Now, this will be later on as the Euclid-Euler theorem. Oh, and for those of you who don't know what a perfect number is, a perfect number is a positive integer equal to the sum of its positive divisors. And in here, he used the function of sigma n, which is the sum of factors of n. And he used two properties of n, and he used those both properties to prove the theorem with the perfect numbers. And also here later in 200 BC, Eratosthenes, a known Greek mathematician, created his own algorithm, also known as the Steve Eratosthenes, which pretty much what it is that he used a 10 by 10 grid, and then he scratched out with 10 by 10 grid with numbers from 1 to 100, and he scratched out all the numbers that have multiples of 2, 3, 5, and 7, and the numbers that are crossed out were considered prime. In the 17th century, Pierre de Fermat discovered a word called as Fermat primes, which is described as a positive prime p, which there exists a non-negative integer alpha with p equals to 2 to the power of 2 to the power of alpha plus 1. There's also Marie Mersenne, who was a Catholic priest. He was the one who discovered Mersenne primes. Also, Leonhard Euler. He also proved in 1737 that the sum of reciprocals of all prime numbers diverges, which equals to infinity. And also Gauss, Carl Friedrich Gauss, created his own theorem when he was a teenager, and he had conjectured that the number of primes below a bound number n was in his notation the integral of the derivative of the n divided by log of n. And there was also a new theorem that was needed to be proved, which is the prime number theorem, or PNT, which states that the number of primes not exceeding x is asymptotic to x divided by ln of x. There were a number of mathematicians who tried to prove these theorems through generations. Starting in 1798 when Legendre conjectured on the size of pi of x, which is almost equivalent to the PNT. The constant 1.08366 only went up to x equals to 400,000. In 1850, Chebyshev made progress towards the PNT as well. And we'll later on see here that it wasn't until 1896 which were two mathematicians, Hadamard and de Poussin, who worked independently, and they successfully proved the PNT, and they did it using Bernard Riemann's work, using the zeta function, which then they proved that they deduced the PNT. Since they did use complex numbers here and complex functions, it was a bit more difficult to understand. And it wasn't until 1949 when Atle Selberg and Paul Erdos gave elementary proofs, which means that they didn't use complex numbers, but it was still pretty lengthy. And in 1980, it was DJ Newman who introduced his own theorem with a much shorter proof to develop a simpler link between the zeta functions and the PNT. And there is still a lot to learn when it comes to prime numbers here. Number theorists, mathematicians, they try to work themselves, not just to verify the theorems, they also try to level up their skills, and they try to understand more when it comes to the math involved. And also when it comes to mathematicians nowadays, they still try to work several ways in finding new prime numbers.
Okay, so now we're at part 2 of prime numbers in cybersecurity, the part about RSA. So here we have the faces behind RSA, the 3 MIT professors who developed it, whose initials are the acronym. They are Ron Rivest, Adi Shamir, and Leonard Edelman. And so they published their algorithm in 1978 in Communications of the ACM. So public and private, asymmetric encoding and decoding. What this means is that this crypto system, is asymmetric, not symmetric. Symmetric would be using the same key to encrypt and decrypt. The way this asymmetric works is you have a public key and a private key that you use to encrypt and decrypt messages. So we have carrot and pumpkin. So if we think about Cinderella, right, where the pumpkin turns into a carriage and the carriage goes back into being a pumpkin. So we can think of it like encryption and decryption. So here we generate a public key and a private key, and then we make sure that whoever we want to communicate with gets the public key. So we can send it through email, the website, forum, just any way they can get access to it. It's fine. This is the public key. It's okay if someone other than the intended recipient knows the public key. Then the receiver, right, plugs in the public key into the encryption software, right? They come up with a message they want to send you, right? They run this key and encrypt the message with this key. This generates the encrypted file, and they send you this encrypted file to you. So a little bit about digital signatures. The idea here is to be able to verify that you want to make sure that you're talking to who you think you're talking to. So the way this works in real life is we sign something with our signature or fingerprints. The way this would work with with RSA is you would encrypt something with the private key and send it off, and someone would open it with your public key. And because this is asymmetric, in order to do it, you have to use the opposite key. So in order to unlock something with the public key, it had to be encrypted with the private key, meaning since only you have access to the private key, right, it's generally an authentic message from you. So prime numbers and prime factorization. So here we have 2 prime numbers, 53 and 59, and if we find the product, it's 2,127. Nothing impressive here. It's pretty easy to do. You can do it on pen and paper. Less than a minute. What about the factors of 3,127? Well, from the previous question, we know they're going to be 53 and 59, and 1 in 3,127. What about the factors of 374,287? Well, we have no previous question here to figure out what the factors are. So we have to do it by trial and error. 1, 2, 3, 4, right? Divided by 1, 2, 3, 4, 5, 6, 7. Keep going on and on and on until we get it. And if we asked you about the factors about this number down here, that's a lot more harder. So that's kind of the idea here, that prime factorization is harder than multiplying two big numbers together. And RSA uses keys from 300 digits to 1,200 digits. So yeah, it's hard for even computers to keep up. So how do we generate an RSA key pair? We choose two large prime numbers, and then we find the product n, right? And we also have p and q, the prime numbers. Phi of n, which is the Euler-Totient function, where we have a prime number, and if we want to find the Euler-Totient, it's going to be that prime number minus 1. So n is comprised of p and q, so that's why we have p minus 1 and q minus 1. That's how we get phi of n. And we have to choose e and d, or e times d mod phi of n equals 1. N and e will be our public key, and d and n will be our private key. Keep it secret, keep it safe, right? It's precious. Make sure it doesn't fall into anyone else's hands. And we'll go over an example right now. So here we have an example. P and Q are 11 and 13. Our product of these numbers is 143. Phi of n is equal to 120. So we have the math here. Then we have the product e times d mod 120. So the product of e times d would be 7 and 103 mod 120. So P and Q we choose, and from the product, phi of n, pretty easy. How did I get e and d? Well, we're going to go over that. So how do we find e? So e has to be smaller than phi of n and coprime with phi of n and n. And since now we could start with 1 and then work our way up, but 1 is a factor of every number, so that kind of just chuck it out. And 2 kind of 2 isn't usually used. We usually start at 3. Just 2 kind of factors a lot of numbers. Like if you're an even number, you're a factor. 2 is a factor of that number. So here we go through it, and we get 7. So that's not too hard, right? We'll get here pretty quickly. Then how do we find d? So d is the extended Euclidean algorithm, and here we start with phi of n, we start with e, and we start with 1. And the point of all this is to get this side to be equal to 1. You might have to go through several iterations, but eventually you're going to get this, which is d. And then in order to encrypt a message, okay, we're going to choose our number, write our message. We want to pick 2. We're going to use our public key and n mod 140, and this gives us 128. How do we decrypt it? Well, we have the public key, the private key. So here we're going to take not the message, the encrypted message we got. We're going to use d, our private key, mod 140, and we have 2. And there we have it. Encryption, decryption, RSA. So the next topic we'll be talking about applications. So stick here for that.
Hello, my name is Melissa Garza. So this is going to be the last part of our presentation, prime numbers in cybersecurity. So by now, Pablo has already spoken about the history of prime numbers, and Miguel has spoken about the encryption and RSA system. So I will be speaking about the applications of prime numbers, or the uses of prime numbers in settings other than mathematics. So there are many applications for prime numbers, and I'm just going to identify a few that I came across when doing my research for this project. So one of the most important applications for prime numbers is the RSA system. And by now we know what the RSA system is and how it works. So the RSA system comes into play when you or I am trying to make a purchase online from a clothing store or any website like Amazon. So in order for you to make the purchase, your credit card information needs to be entered on the website. And so for it to be sent to the merchant, your credit card information needs to be encrypted so that it doesn't get into the hands of anybody else. And then once it reaches the merchant, it becomes decrypted. And this is the same for when you are trying to access your bank account to see where your bank statement is, or to see how much money you spent, or the purchase, or to make sure that the purchases you made are the same. So another application, another thing that I came across when I was doing research for this project was how prime numbers are in nature. So we're gonna talk about, so I found an article that talked about how the cicadas used prime numbers to maintain their survival. So according to a scientific research, it was found that the cicadas use prime numbers to come out of their burrows underground and lay eggs. Cicadas will only leave their burrows in intervals of 7, 13, or 17 years. It has been theorized that they use prime numbers so that predators don't evolve and prey on them. So the cicadas' predators are birds and wasps and other animals, and they have shorter life cycles than the cicadas, roughly about 3 or 4 years. And for every 3 or 4 years, the predators come out to hunt, and so they avoid being eaten by waiting underground for any prime number of years. So why prime numbers? Because only prime numbers won't overlap with the life cycle of their potential predators. So another application that I found, that I came across, was that, and it's apparently not very well known, is how prime numbers involve the search for and communication with extraterrestrials. So an astronomer and science author named Carl Sagan demonstrated this interest in a film he made named Contact. In the film, the main character is with a team of hers that are attempting to find extraterrestrials, and they end up picking up a signal from a nearby star Vega. When they tune in, well, they come to find that the messages contained a sequence of prime numbers 2, 3, 5, 7, and 11. So they believe that this was the extraterrestrials trying to communicate, because what prime numbers are fundamental to the generation of natural numbers. So this is all that I have for our presentation. So this will conclude our presentation. Thank you for listening.